Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we are going to implement the Gaussian process techniques that we learned in past three videos on a real world data set. And this is going to be data set on greenhouse gases. So we'll try to predict the concentration of carbon dioxide, methane, and nitrous oxide in next 10 to 30 years. And the data source is listed here. I'll put the link for data source in the description of this video. And many thanks to the authors and the Mauna Loa Observatory and NOAA for making this data set available as open source so that we can use it. So greenhouse gases, you're probably aware of this, have functions to keep harmful radiations from the sun away from Earth, as well as uh, keep some of the heat from the Earth's surface contained around in the Earth's atmosphere. However, if the concentration of these gases continue to increase, then it can start to heat the Earth's surface, and that can have a negative impact on the climate of Earth. And here, the data that we have for carbon dioxide, we see that the concentration was 315 parts per million in 1958, and now it is at 417. So, if the rate at which this continues to increase continues, then the temperature of the Earth's surface, which now is at around 1.02 degrees centigrade, could increase by 2 degrees. And the this is kind of about maybe for up for debate what concentration of carbon dioxide that would be equivalent to. But from what I've read, it if it crosses around 450 or 470 ppm, maybe that's the time when the temperature could increase by 2 degrees. And the one of the immediate impact will be rise in sea levels by about 0.66 feet or zero point 0.2 meters or greater than that, and that's going to affect life on Earth negatively. And I've put the links below here as well, so if you want to check them out, they have more information on this. So what we are going to do is we will see at what year from now we would be reaching this temperature. So the data that we'll analyze today is not just an exercise, but I think that it also has, we'll be able to see some real world consequences. Although I'll put a disclaimer as well that the predictions that we'll do in this video um, may not be accurate. So this is just as an exercise to learn Gaussian processes. And for data, when you download the files, you'll see a file, text file or CSV file with all the commented lines. What I've done is manually gone ahead and deleted all the text and just kept the columns that are here. So once and they do have column names. For the first two columns there are no column names, so you can just add them manually. And the two columns that we'll end up using is just this column, which is the decimal date, and the monthly average, that's either parts per million or parts per billion depending on the gas that we are looking at. And this is the cleaned up file which I've just manually done. That this is for carbon dioxide, this is for methane, and this is for nitrous oxide. So let's get into Jupyter Notebook and start coding. Here in Jupyter Notebook, I have imported all these libraries. We may not use all of them, but I've put them here anyways. And then these are the versions that are installed on this machine. And here are the citations for the data source. And also the code, I've referred to this code from Scikit-learn docs, which is the Gaussian Process Regression or Mauna Loa CO2 data, the code by Jan Hendrik Metzen. So definitely want to check that out if you want to look at the exact example that's in the docs as well. So the very first prediction that we are going to work with is the CO2, and for this we'll use the file that we have downloaded. So I've downloaded the file to my desktop, so I'll just create the path to that desktop, and then we read the data file. So data is equal to pd.read underscore csv, and then path plus name of the file. So this file name was co2 underscore monthly. This is Mauna Loa Observatory .txt. In the introduction, I said it was a CSV file, but it's a txt file. But still, we can open it. Delimiter. So the delimiter here is space, and so we are going to use a regular expression, which is \s plus to split the uh, split the columns, and then we can look at the couple of rows from the data set. So here, as you can see, the year and month, it's already been converted to decimals that we are going to use. And from all these columns, I've just focused on the average column. So if you are interested, you could try out other columns as well and see how um, how those results look. So first, what we'll do is uh, get the data into X and Y. So for X, we have data, which is decimal, and so so that's the actual. This is the X-axis, and that's the year. And I'm going to convert that to an array because we need that in that format later on. So np.array, and why not go ahead and reshape it as well to a column. And next we have the target column. So np.array, again this would be data, and we have the average column. So we have that, and again we could reshape it, or for now I'll just leave this column as is, and we can look at the shape. So print x.shape and y.shape. So we have around 757 records for this. And for the test set, what we are going to do is, for the prediction part, we'll create data later on based on the x values we have, and just predict the y values. So the very first one is looking at creating kernel. So if you remember from the previous video on the kernels, we talked about combining different kernels, and that's exactly what we are going to do here. So we'll create one kernel K1 that is going to be RBF kernel. So we have RBF and length RBF, and we have the length scale set to 50, and then we'll also add this parameter here to 50.0. And if you are wondering how do I know the values that need to be input for these parameters, and the reason why I know this is because I've tried several uh, parameters before creating this video. So these seem to work well, and these are not the final parameters that would be used in the model. These are the ones that would get optimized as well. So the next one, second kernel, is a combination of two kernels. So we have the RBF kernel multiplied by the exponential sine squared kernel. So multiplied by exp sine squared length underscore scale is equal to 1.0, and then periodicity. So the RBF kernel is good for the smoothing and increasing trend, and then the exponential sine squared kernel is good for looking at the seasonality effect. So if there is a monthly wiggly shape to the curve, then this would be able to um, model that. And we'll set the periodicity underscore bounds to fixed. So that's the second kernel. Then the next kernel we can create is a rational quadratic kernel. So these are the kernels directly from the docs. I've tried to use them and see how they work. And they also have a reference paper. I forgot to mention that here. So all this combination of four kernels comes from that paper. And the next is rational quadratic, and this is length scale of 1.0, alpha is equal to 1.0. So right now we are just initializing the values for these kernel parameters. Next we have next is a kernel for noise. So here we'll use RBF. We have RBF plus white noise kernel. So plus, let's add here white kernel. And so for each of these we'll now add the parameters in there. So we have 0.1 squared for RBF, and then add the length underscore scale is equal to 0.1, and then we have the white kernel. So this is noise level, set it to 0.1 squared, and next we have noise level bounds. So the default is 1 e to the power minus 5 to plus 1 e to the power 5. And we could leave it as is, or we could add that here. So in this example we are going to set the lower bound to the default, but then the upper bound will change it to np dot infinity. And with that, now we can use the sum kernel that we discussed in the previous video. So we simply can add all these kernels, k1 plus k2 plus k3 plus k4, and so now we have the final kernel ready. So here this needs to be a multiplication sign there, and again I missed a multiplication sign right here. Okay, so now we have the kernel, and we can use this now in the Gaussian process regressor. So we'll create a variable gp is equal to Gaussian process regressor, and here we have kernel is equal to kernel, and alpha is equal to 0. We'll set normalize is equal to true, and perform gp.fit on x comma y, and we can go ahead and print the log marginal likelihood as well. So first we'll get the name of the kernel, so learned kernel, and this is the gp.kernel, and then next we have print the log dash marginal dash likelihood, and this is that the 0.3f 0.3f, and gp.log underscore marginal underscore likelihood gp.kernel underscore dot theta. So this code will type it once and we'll be using this over and over, except some changes to the kernel part. Now if you run this cell, there should not be a comma there, and we have normalize, I would say the kernel, and so in this particular normalize is equal to true, normalize y is equal to true. So once the fit is done, we should get a log marginal likelihood values. And in this case, for fit, we did not specify if how many runs it needs to do to get the final result or get the optimal parameters. So here in the next section, we'll add that particular value. What okay, so we have log marginal likelihood of 2300, and let me copy this and look at the help. Okay, so this n restarts optimizer, this is set to 0. So had we set it to a value say 3, then it would run 3 times to before it finds the optimal values for the parameters that we are going to now use to perform the prediction. So here for predict, we will create the x test. So we'll denote it by simply x underscore is equal to np.linspace x.min. We'll take the minimum and maximum value of the x that we have and extend the range. This is plus 30, and we can get about 1000 points from there, and again reshape it. So with this we can now print the shape. So x underscore dot shape, and we can also, why not look at the type of the object we are creating. So we have an array of 1000 rows and 1 column. Now with this information we can predict. So y underscore pred, y underscore standard deviation, we need that to plot those that band of confidence interval around the, or standard deviation band around the predicted values, predicted curve. So gp dot predict, we have x underscore and return underscore standard deviation is equal to true. And once we run this, we now have the predicted values. So with this, we are now in a position to plot our findings. So let's create a plot. Figure is equal to plt dot figure, fig size is equal to 15 by 5. We can get a nice rectangular plot. Plt dot scatter x comma y, c is equal to k, and we have alpha set to 0.55. So the main data would be the dots. Then plt dot plot x underscore y underscore pred, and this is going to be a line. And then we have plt dot fill between. Here we need to specify the x underscore, and we have that there. Next we have y underscore pred minus y underscore standard deviation, and then y underscore pred plus y underscore standard deviation, and we can set the alpha value again to 0.5, and color we can set it to Alice blue, same as what we had last time. And then we can limit the x and y range. So plt dot x limit x underscore dot min and x underscore dot max. So we have the xy limit for that. And finally we have the labeling to do. So x label would be the year, and we have y lab plt dot y label, this is going to be parts per million, that's the CO2 concentration. And plt dot title, we have carbon dioxide. Okay, and we can here look at the plot. Plt dot show, and see what we get. Y label. Okay, so we have a really nice plot. As you can see, the confidence interval bands are not visible, so let me change this to maybe a darker color. Just put a K there. Okay, so now we can see that these. Okay, let's do one more thing. I'm going to copy this and change the x min. So we'll go from 2000 maybe 15 to 2025, and the reason is I just wanted to show up close how the data is. So as you can see, we have these dots which are the actual values, then we have the line that is the predicted value, and our data ends right here where these dots end. And even after that, with the Gaussian process, we are able to predict the future trends really nicely. And we can see this trend, the wiggly trend, it continues with this model. And as we go farther from this data, we start to see that increase in the standard deviation band around the predicted line. And if we are here at 2021, and if we go all the way up to 2040, so that's 20 years. And we talked about looking at the ppm in 10 to 30 years, so let's look at 540. So 540, let's say it's about here. So we are at 540 in maybe around 10 years. We reach 575 uh, by 2040, 20 years, and it continues to increase. So uh, this would be year 2060, I think, yes. And by 2060, it could reach close to 500, and that's going to be uh, probably tough time for the environment. If this is correct, this could be completely wrong. It could come down right here if we have, we don't know that. Okay, so that's an example of how Gaussian processes can help us analyze a time series uh, to get this particular prediction. One thing as an exercise I would encourage you to try is work kind of working with these four kernels, changing the parameters, see what happens, changing the values, and see if it makes any difference, or adding or removing kernels, does that make a difference? For example, here if I remove this noise kernel, or let's say if I remove the K2 kernel, which is for seasonality, and if we run this again and create the plot, we would get a completely different plot as compared to what we had before. So uh, the seasonality effect, maybe we'll lose that because we removed the kernel, we removed the exponential sine squared kernel from the model. So while that is running, uh, we can look at uh, some of the parameters that are in that kernel. So this fixed can also be changed. So we can specify bounds similar to the bounds that we have specified here for the noise level. And we can also change the periodicity. You can try increasing or decreasing it. And again, we have the rational quadratic kernel here, which we may not use for the other two gases. We'll see. So this is still running. I'll come back when this run is completed, and then we'll look at the results. Okay, so here we have the run is completed, and as you can see in this particular plot now, the seasonality effect is gone. So let's zoom in on a portion, again the same area, 2015 to 2025, and Here, as you can see, after the training data ends, the line becomes essentially a straight line as compared to what we had earlier. So now if we include uh, the kernel K2 in there, I run this again, we should see the seasonality in there. So I'm going to create a new cell, and uh, we'll run this cell again and compare the plots from this and the previous run. And hopefully we should be able to see the difference that I was talking about. Again, I'll cut the video here, come back after the run is done. Welcome back. And here, as you can see, there's a big difference in how the plots look. So you can see this trend continues when we have that kernel, and it's not here. So that's the importance of knowing what combination of kernels you want to add to the model, so that it captures the trends in the data. Now let's look at the next data set for methane. We have methane, and for this, again the path is going to be same. uh, I'll change the data file. So data is equal to pd dot read underscore csv path plus the name of the file is ch4 underscore mm underscore gl dot txt, and again the header is equal to 0, delimiter is equal to space, so backslash s plus, and let's look at the head, data dot head, and see what columns we have. So again we have the same columns. We'll use the decimal and the average column. So in this particular part, what we are going to do is copy most of the code from the earlier exercise. So we'll copy all these values, or why don't we copy the entire cells? So I'll copy from that cell right here all the way up to this particular plot. So copy and paste it here. And the main difference is going to be looking at what the kernel looks like. So we'll run this, and this time we just have 450 records. Now for kernel, I've tried different kernels, and some of them uh, worked, some of them didn't work. So this is the final combination that seems to have worked uh, based on the type of data we have here. So K2 is equal to, and we can look at the data. Actually, we should. So let's plot that plt dot scatter x and y. That should do it. So that's how the data looks like. We can extend that. So figure is equal to plt dot figure fig size is equal to, let's know, 15 by 5. So we can spread it out. So as you can see, there is seasonality in here as well. Alpha is equal to 0.5. So this is what we want to capture. So we have this periodic jumps, and not all the jumps are same. For example, here this is little different. Here this part is little different. So we need to account for all of that. So the kernels that in this case will create the RBF and exponential sine squared kernel, because to capture the seasonality. So 2.0 in the square of that into RBF, and here we'll have the length underscore scale set to 10.0, and or maybe 100.0, and then multiply this. So multiply this by exponential sine squared kernel. So exp sine squared length underscore scale is equal to 1.0, periodicity is equal to 1.0, and periodicity bounds is equal to fixed. So this will capture the seasonal component, and then we have I'm calling this k, let's call this k1. We have k2. So k2 is going to be the white kernel with RBF. So 0.1 into square of that, square of that into RBF. Again, length scale is equal to 0.1, and then to this we are going to add the white kernel. So we have white kernels with a capital K, and here we specify the noise level is equal to 0.1 squared, and then we'll specify the noise level bounds. Noise underscore level underscore bounds is equal to 1e for minus 5 to 1e to the power 5. I think this is the default value for this kernel as well. And after this, the third kernel is so here I've used another again. There are two exponential sine squared kernels. So let me copy this, paste it here. Oh, let me copy this again. Copy and then paste it here, and let's call this k3, and the values for this kernel are 2.0 for RBF, and then this scale set it to 1, and then the length scale, periodicity, and the bounds for the exponential sine squared kernels stay the same. And finally we'll add them. So kernel is equal to k2 sorry k1 plus k2 plus k3. So those are the kernels we have for this particular set of data. And now the rest of the code uh, should work as is. So we'll run this to get the values for parameters. We'll run this without any optimizer first, and then we can add the n underscore restarts underscore optimizer is equal to 3. So we'll run that as a next loop in this part. And while this is running, let's go ahead and look at the test part. So we have x underscore is equal to np linspace min max plus 3 new axis. Okay, so that looks good. So we'll leave this as is, and this should also be, and this should also work as is. So let's go ahead and run all the way up to the plot. And here, as you can see, we now have, so these we have a marginal likelihood of 1100. It's much lesser than the previous plot that we saw for carbon dioxide. So maybe there is room for improvement here. And as you can see in this case also, we were able to capture this seasonality in the prediction. Although as compared to carbon dioxide, we see that the standard deviation seems to grow pretty early on, as uh, maybe in 2-3 years as compared to what we had for carbon dioxide, where the bands were very narrow for at least 4-5 years. So maybe that's a place where optimization could help. Now here what we can do is we can try running maybe 3 runs for the optimizer and see if that helps get the best parameters, and if that changes the plot. And while that is running, uh, we'll set up the code for the last part of this, which is looking at the nitrous oxide. All right, so now we have the plot with the optimization for 3 runs, and we still see that the uh, band for the standard deviation is still starts very early on to broaden. Even though it is still good prediction, we can see that uh, this should be methane. Let me change that title there. And this is parts per billion, not million. Okay. So here we can see for methane, again, the trend could continue to rise in the next 20, 30 years. And yep, so that's there. Next, let's look at nitrous oxide. So I've typed this here. Let's convert that to markdown and have that heading. And I'm going to copy this exact same code down below, and we'll change the kernel and the name of the file. Rest everything should stay the same. Here we have the name of the file. In this case is N2O, and that should work. So let's run this, and here we just have what 239 records, and this is how the data looks like. Here again, if you see, there is periodic wiggle, so that's the seasonality. Maybe that's the monthly variation during a year, and then overall we see that it is a straight line, and it's continuing to increase without any sign of slowing down or tapering off. So the prediction, we would expect that it goes along the same direction. So with that, now we'll look at the kernel that would work here. So for K1, we'll use the same RBF kernel with the exponential sine squared. And for K2, we have the RBF kernel with white noise. And here, what I'm going to do is change the bounds. So this bound to np dot infinity, and then for the last one we have the same RBF kernel, except for this case the value for length scale I'm going to set it to 100 instead of 1, and then for length scale periodicity everything could stay the same. Now with just these minor changes, let's run this one and run the fit, and here we already have 3 restarts for the optimizer, and okay, all bounds are finite. So if you see this, the reason why we have this error is uh, the bounds need to be finite, and here I've specified that this bound is infinite, and that's why we have that error. So we can change, we can set it to 185, and if you get a warning, we can increase or decrease that particular bound to 1 e to the power 9 or 1 e to the power 6, and this should be parts per billion, and instead of methane the title here would be nitrous oxide. Nitrous oxide. So I'll let this run and come back when the run is done. Okay, welcome back. Here we have the run completed, and as we can see, the trend seems to continue, and looks like here it tapers off after the year 2040. That's after 20 years from now. uh, that's just a prediction. We have a broad standard deviation margin, error margin there, so it could go up straight that direction, or it could come down here as well. So one last point, we can zoom in and look at the seasonality effect there. So if we again go from the year 2015 to 2025, 2015 to the year 2025, and run this. So here we can see that there is, and let me remove this part. Okay, so it's less stretched out, and we can see that the wave continues even after the training data ends. So that tells that the model is able to capture not only the overall trend but also the seasonality within that, and also has the standard deviation that increases after 14 years. So that particular region of prediction is more confident as compared to the regions after this part. So that was it for this video. I hope in this project you not only learned how to implement Gaussian processes on real world data that includes a time series, but also in the previous videos you got an intuition about what happens in the background when we run the Gaussian process regressor code. We looked at the intuition starting from what is Gaussian, and then looked at the effect of covariance matrices and how that enables us to find similarity between points. And then we looked at what are the different capabilities made available to us in the scikit-learn that we can use very easily with very little lines of code to get a very powerful prediction model done, such as we see here. And uh, and here again, what I wanted to emphasize is during the periods where we have the training data available, we can see that the standard deviation is or pinned to the data points, and therefore we do not see the gray band in this region. It starts only after when the data points disappear. That's after the year 2021, and that's because now the distance between the data points and the prediction is increasing. The observed data and the new test data, the x star is increasing, and therefore the values for those particular data points in the covariance matrix are now decreasing when we go on this side. That's kind of signifying that they are moving farther and farther apart. So I hope you enjoyed this series on the Gaussian processes. I know we didn't talk about the classification part of this, or I'll think about adding that as a future video. Until then, please like, share, and subscribe. If you have any comments or suggestions, please let me know in the comment section below. And if you like this video, please let me know, as it helps me stay motivated to create more content for you all. Thank you.